Conventional incinerators can dramatically reduce waste volume and eliminate some toxic compounds. However, the fly ash left behind is a serious concern for secondary environmental pollution. Ash's recirculation combustion technology breaks through this limitation. By reintroducing fly ash into the combustion system, the process uses high-temperature decomposition to effectively destroy persistent hazardous pollutants. A key aspect of this technology is that we concentrate on the secondary solid waste and find a way to circulate the persistent organic pollutants back to the primary combustion chamber. We then mix them with our waste or waste liquid, inject them, and perform a second round of combustion. This process ensures that the concentrated pollutants are broken down once again. Conventional air pollution control devices often accidentally generate more dioxins. This happens when chloride ions and unburned carbon particles react with catalysts at temperatures between 200 degrees Celsius and 400 degrees Celsius. However, the Sustainable Energy and Aerosol Technology Laboratory, led by Professor Sheng-Lun Lin, has successfully broken this harmful reaction chain. Using techniques like flameless combustion and uniform temperature distribution, they have significantly reduced the emission of this poison of the century. This new combustion technology actually creates a flameless environment inside the combustion chamber. Without a visible flame, the entire space becomes a single, continuous reaction zone. This flameless or volumetric combustion significantly expands the reaction area, making it more uniform and boosting thermal efficiency. Overall, the entire process is a sophisticated cycle of combustion, pollutant control, and the concentration and recirculation of pollutants for complete destruction. We are quite fortunate in our lab because we have access to a waste incinerator right here at National Cheng Kung University. This allows us to conduct scaled lab experiments. By controlling environmental conditions in the lab, such as temperature, catalyst composition, and combustion efficiency, we can then apply these parameters to a real-world setting for testing. Unlike traditional equipment that only handles a single type of pollutant, ash slag recirculation technology takes a holistic, system-based approach. It re-decomposes persistent organic pollutants in the fly ash, boosting dioxin removal efficiency to over 99%. This process also transforms hazardous bottom ash into reusable industrial waste. With the fly ash now being recirculated, the remaining bottom ash has a very low concentration of toxic substances, falling below the standard for hazardous industrial waste. Since it's now classified as general industrial waste, it can be directly stabilized and reused. This saves a significant amount of money in post-treatment operational costs and also reduces CO2 emissions. We estimate that these post-treatment expenses can account for up to 40% of a plant's total capital. So with this technology, we can effectively cut our operational costs by about 40%. With the support of the NCKU Innovation Headquarters, we have identified key entry points for applying this technology, developed more efficient solutions, and built a solid patent portfolio. Today, the technology has already secured patents at various stages internationally. To bring this into real-world use, we'll rely on the NCKU Innovation Headquarters, its networks, industry links, and practical support. Facing stricter international emission standards and new incineration challenges from emerging materials, This technology demonstrates a high degree of adaptability. By integrating carbon capture and resource recovery, it not only solves current pollution problems, but also opens up new opportunities for the circular economy and carbon neutrality. The cleaner you process waste or organic matter, the higher the proportion of CO2 becomes. We use a modified sorbent to capture CO2 from the flue gas, converting it into a solid. This solid is then trapped by a catalytic filter material, which in turn processes the remaining pollutants. We are now trying to extract this CO2 sorbent directly from fly ash and bottom ash. This will be the focus of our next development phase.